Now we're going to start with momentum. We're starting with section 9.4. And so momentum is P equals mv. V is a vector, P is a vector. You know that for a system of particles, it works the same. This is for one object, but if you have a bunch of objects, it works the same way. And sometimes it's capital P, M, V, time, and if you add up all the M and V of the whole system of particles, then it works the same way. You can talk about the momentum of any system. As long as you define this is the system I'm talking about, it can include as many objects as you want. And then the rules for momentum work. We can also relate it to the net force, right? Let's think about it this way, right? What is mv? mv is dx dt, right? All right, so let's look at force. F equals ma, right? And what is a? M dv dt. But if we multiply dv by m, then what we end up with is d mv dt. So the force is actually related to the rate of change, rate of change of the momentum. Right? So force, let's put arrows on our vectors here. The force of an the net force on an object is equal to the derivative of the momentum. Okay, and actually this is how, as long as m is constant, by the way, this is actually how Newton wrote his second law, that the net force is equal to the time rate of change of the momentum. He didn't say F equals ma, he said F equals dp dt. Just historical note there. And the same is true for a system of particles, right? F net is going to be equal to d capital P dt. So then if we have a graphical analysis of momentum, if the momentum graph looks like this, right, P and T, the force graph then is going to look something. So this is positive slope. This is the place where the slope is 0, so it'll be like that. And it's negative the whole time, and then eventually we have negative. So this is the place where it reaches the most negative and then goes to 0. So it's going to look something like this. Right? This is what the force time graph would look like given this momentum time graph. Right? Conservation of linear momentum. Again, if the net external force acting on a system is 0, then the total linear momentum remains the same. All right, you're familiar with this, and this is true for each of the vectors, right? Horizontally, vertically, you can look at it all these different ways. Just like a projectile, the net force vertically is gravity, and so you're going to see change in momentum vertically because there is an external force. Horizontally, there's none. So we can think about even something like projectile motion in terms of conservation of momentum. All right, so different types of collisions. You've got elastic, completely inelastic, partially inelastic. You're familiar with all this stuff, right? Momentum and kinetic energy in collisions. Momentum is always conserved. No matter what the collision is, elastic, inelastic, the total momentum is always conserved. The total kinetic energy may not be conserved, though. That's the difference between elastic and inelastic and that kind of thing. Again, you know this, if the kinetic energy is conserved, it's called elastic. If it's not conserved, then it's inelastic, which could be totally inelastic, where the things stick together, or partially inelastic, where they don't stick together, they do bounce off, but some kinetic energy is still lost into some other form of energy, usually heat or something like that. And you have some diagrams here, all just illustrating conservation of linear momentum. Two ice skaters coming together. Collisions, again, can be elastic, completely inelastic, partially inelastic. Impulse. I don't know what letter you've used in the past for impulse, but in this class, we're going to be using J. And J is not terribly uncommon to see. It's just sometimes not introduced in introductory physics or first-year physics because it's a little confusing. So J, J is interesting. Impulse is interesting, and it can be really confusing because it has its own name, impulse. This is one of the few places where we say the change in something has its own name. Impulse, all it is change in momentum. That's it. Anytime you hear impulse, you think impulse, you see it, J, just think change in momentum. In fact, it might be helpful that anytime you see it, just substitute delta P. Substitute that in there to help you think about it. Now, since this is the change momentum, and we also know that J is going to be equal to, from time initial to time final, the integral of force with respect to time. Right? Because force is the derivative of this, so the antiderivative of this will give us the change in this, right? And so let's look at this in terms of units as well. We want to keep units in mind here. According to this, J is going to have units of Newton seconds. Right? How does that work out? A Newton is a kilogram meter per second squared, again, times seconds. So this is a kilogram meter per second. Mass times velocity. Right? So it works. So again, if you forget the unit, if you forget this, like, oh, the impulse, is that the derivative or the integral of the force, just think to yourself, this, what are the units? Units on force, newtons. So if I multiply that by seconds, multiplying units is like, that indicates taking the integral. Taking the derivative is when you're dividing. So if you had this and you wanted to get to force, you're like, okay, well then this divided by seconds is going to give me the right units for force. Dividing is like taking the derivative. Okay. And so then we have some graphical representations here of the impulse, right? The impulse is equal to the area under the curve, and if you can estimate it with a rectangle if you have to. This comes from Newton's second law. Again, like we said, I took it down already. Newton's second law is, all right, other important information there. All right, so now we have an example. Let's take a look at it. So in this problem, the way I wrote it was that VI is 30 meters per second and VF is negative 37 meters per second. I wrote that because we find out here that it's struck and then it's moving in the opposite direction. So I'm just going to make the initial direction positive and the final direction negative. First question is asking, what is the impulse of the bat on the ball? So let me, just one more thing here. So we're saying initially it's moving this way, 30 meters per second, and then afterwards it's moving that way at 37 meters per second. Right? It's coming this way, it hits it with a bat, and then it's moving in the negative direction that way. So part A, what is the impulse? Well, impulse is delta P. Delta P is going to be m, same mass, VF minus VI. All right, change in momentum. I just factored out the mass there. Okay, skipped a step algebraically. And so when you plug in the numbers, this is going to be the 1.5 or the 0.159. This is negative 37, and this is 30, right? So negative 37 minus 30. And when you do all the calculations, you end up with negative 10.65 Newton seconds. We can put it in terms of Newton seconds. That's okay. All right? That means the net force on it was in that direction, right? Think through what that means. And we would expect that because the change in the velocity was in that direction. All right, so part B now asks us, what is the average force of the bat on the ball? Again, we're looking for average force here because in reality, a bat hitting the ball, it's a constantly varying force. It starts off small and then a lot and then a little over a very small period of time. So we're just asking for the average force, and that saves us from having to use calculus. So J equals Ft. We know J from this, and we know the time was just given to us. So the force is the impulse divided by the time, so negative 10.65 Newton seconds over 1 millisecond, so 1 times 10 to the negative third seconds. Well, that gives us negative is it 10,650 newtons. And that's good. You can see the units, the seconds cancel out, and we're left with that. Okay, in example 2, we're given this function of the force. We're saying given this function of the force, we want to know what is the impulse on the body from 0 to 3 seconds. If we have the force function, we don't know what the initial and final momenta are unless they're given to us. So what we can find here is just the change in momentum. But what is the change in momentum? It's the impulse. All right. And here we're using calculus. And so the impulse, as we saw before, is the time integral of the force function. And so this is going to be from, let's see, let's just say Ti to Tf of 2t squared plus 3t dt. All right, so this is going to be 2 over 3 t cubed plus 3 over 2 t squared from 0 to 3 seconds is what the time that's given to us. So we plug these numbers in, and when I want to go through, take your time that way, but when you plug the numbers in, you should get about 31.5 Newton seconds. Okay. Example 3 is similar, except that here we're given the momentum function. And here we want to know the net force on the body at 3 seconds. First thing we do, take the derivative, and we get the force function as a function of time, and then we just plug in 3. So when we take the derivative of this, F is dp dt. So the derivative of this is going to be 4t plus 3. Okay, so then the force at 3 seconds, we just plug 3 into this, right, and we should get 15 newtons. So this is example 3. Okay. The first example 3. I guess we have 2 example 3s. So again, impulse linear momentum theorem is that the change in momentum is equal to the momentum, or the impulse, and in 3 dimensions, so we can write this down. This is true that the change in the momentum in the x direction is equal to the impulse in the x direction, the y direction, and the z direction. All right. This one is just a repeat before. So now the second example 3 with a 1,000 kilogram car. Okay, so here we've got 2 cars moving along the highway, both moving east, so they're both positive velocity here. This one is moving slower than this one. It gets rear-ended. And the 2 stick together. It's perfectly inelastic. So now we want to find the final velocity of the wreckage. So this is going to look like this. P1 plus P2 equals P3. And it's all in the same direction, so I'm not going to write the vector signs. We can deal just with magnitudes now. And so this is mass times velocity plus mass, so 1,000, times velocity equals, and then the final mass, the total resulting mass, this should be 4,000 kilograms times VF. And that final velocity is going to be about 27.5 meters per second. All right. Simple problem, something you could have done last year for sure. So now in this problem, we start off knowing the initial velocities of 2 balls, and then we want to know the final velocities of these 2. We know that it's elastic, so that means that the kinetic energy is conserved and the momentum is conserved, but we don't know either of the final velocities. Ultimately, the question asks for what is the final velocity of the 1 kilogram ball. So that's what we're going to try to find. But So because this is elastic, we can write two equations. We can write the momentum equation, right? M1 V1I, which is what I did here, the initial velocity of this ball, plus 0, right, because the momentum of this one is 0 to start with, equals M1 V1F plus M2 V2F. All right. And then these are the two things I don't know. All right. And then, let's see, for energy, this is the total kinetic energy to start with, and that's going to equal 1/2 M1 V1F squared plus 1/2 M2 V2F squared. Okay, so let's plug in some of the numbers because we're dealing with simple numbers like 1 and 4 and 10, so we can put in some of these things. This turns out to be 40. This is going to be 4. I'm just going to call this VF now because I'm plugging in the numbers for V1I. Or sorry, so I'm going to call this V1 plus this is just now V2. That's 1 there. Now I'll plug in here, so this is going to be 1/2 of 4 times 100, so 200 is 2V1 squared plus 0.5 V2 squared. And so I've got this, and I've got this. I've got these two equations. And so what I'm going to do is I'm going to solve for V2. Right, so here V2 equals 40 minus 4V1. Now I'm going to plug this into here. So I'm going to have 200 equals 2V1 squared plus 0.5 40 minus 4V1 squared. Right. And so this is getting pretty ugly. Where did that 0.5 go? Oh, I see what I did. Okay, so to get rid of the 0.5, we're just going to say 400 equals 4V1 squared plus 40 minus 4V1 squared. So now I have one unknown and one equation here. And when you solve this, turn it into a quadratic and set it equal to 0, you get 0 equals 20V1 squared plus negative 320 V1 plus 1200. You can factor out 20, believe it or not, and so you get V1 20 times V1 squared minus 16V1 plus 60. This, you can factor this, right, because 10 and 6, negative 10, negative 6. So 0 equals 20 times V1 minus 10, V1 minus 6. And so then if V1 is equal to 10, so if I plug this in here, if V1 is equal to 10, then V2 has to be equal to 0. And that doesn't make any sense, because if these two collide, what I have there is basically this one just continuing straight through, and this ball not even moving now, because this still has its same initial velocity. But if V1 is 6, then V2 is 16 meters per second, and that looks better. Now that was a lot of work, having to go through and solve two equations and use quadratic formula, and that's why in the next lesson I'm going to show you a shortcut. There's a magic formula for dealing with problems like this: elastic collisions, two bodies, and not knowing either of the final velocities.